Hello! In this video, I'm going to prove that there are no non-abelian simple groups of size 90. We're going to do this by way of contradiction. I'm going to assume that G is non-abelian, simple, and of size 90. Now, since G is non-abelian, I would like to note that the center of this group is not the whole group. Because the center, if it was the whole group, G would be abelian. However, we do know that the center of a group is always a normal subgroup of G. And if we're assuming that G is simple, then it has no non-trivial normal subgroups. So if the center is not equal to the whole group, then the center of the group must actually be equal to E. Let's hold that as a side thought, and we will come back to this point when it becomes helpful to us in the proof. In the meantime, I would like to study how the Sylow theorems can be used to help us here. Notice that 90 is simply 2 times 3 squared times 5. And if we count the number of Sylow 5 subgroups, by the third Sylow theorem, there would be 1 plus 5k of those, which would need to divide 18. That gives us the fact that the number of Sylow 5 subgroups of G would have to either be 1 or 6. And similarly, the number of Sylow 3 subgroups of G has to have the form 1 plus 3 times, say, L. And that would have to divide 10. And so the number of Sylow 3 subgroups is either 1 or 10. Now, since G is assumed to be simple, we should not have only one Sylow 5 subgroup or only one Sylow 3 subgroup, because such a subgroup would be normal in G. And that would therefore contradict the simplicity of G. So we can now pretty confidently assert that the number of Sylow 5 subgroups must be 6, and the number of Sylow 3 subgroups must be 10. Let's take that information. I will recopy it here. The number of Sylow 5 subgroups is 6, and the number of Sylow 3 subgroups, let's say that that is 10. I'm now going to consider a couple of possibilities here. The first possibility is that the Sylow 3 subgroups, each of which has size 9, by the way, let's suppose that they all intersect trivially. So let me make sure that this is clear. Let's let P1, P2, and so on up to P10 be the Sylow 3 subgroups of G. We have 10 of them by assumption. We're going to assume that we have 10 of them. And I'm going to consider a couple of cases. The first case is that, let's suppose that they all intersect trivially. So case 1, let's suppose that Pi intersect Pj is just simply E for all I not equal to j. In this case, we can do a familiar counting argument whereby each one of my Sylow 3 subgroups, which has size 9, contributes 8 non-identity elements to a total count of the group itself. There would be a count of 8 elements in each one of these 10 Sylow 3 subgroups, and if we're assuming that these are all disjoint subgroups with a trivial intersection, that would actually give us 80 elements among these 10 Sylow 3 subgroups. So in this case, we get 80 non-identity elements in the P sub i's. So these 10 Sylow P subgroups, Sylow 3 subgroups, each have 8 non-identity elements in them. And if none of them are overlapping, if we take case 1 to be that they are all intersecting trivially, then we would produce 80 non-identity elements. At the same time, I have 6 Sylow 5 subgroups. And if I give those names, say Q1, Q2, up to Q5, if these are the Sylow 5 subgroups of G, they all have 5 elements in them, 4 of which are non-identity elements, and they have to intersect trivially because they have a prime size. And so these guys would produce a total of, I'm sorry, there's 6 of these. I said 5. There are 6 of these Sylow 5 subgroups. Each of those would have to produce 4 non-identity elements, and that would be 24 non-identity elements in these Qs. The Qs would contribute 24 non-identity elements. The Ps have already contributed 80, and that's already more than 90 elements, and that is a contradiction. So this is too many elements, and that implies that we have a contradiction. That implies that we have a contradiction. In case 1. So what we can assume is that somewhere along the line, there must be a couple of these Sylow 3 subgroups that do not intersect just at E. Let's write down case 2. In case 2, for some I not equal to j, the intersection of P sub I with P sub j is not trivial. On the other hand, it is a subgroup of both Pi and Pj, which are subgroups of size 9. So if this is a subgroup of something of size 9, then its size must divide 9. So the divisors of 9 are 1, 3, and 9. But we're saying right here that the size of the intersection is not 1. And if the size of the intersection was actually the full size of the individual Sylow P subgroups, which is size 9, if this intersection was size 9, it would mean that Pi equals Pj, right? So if the size of this intersection is equal to 9, then actually the 2 subgroups are the full Sylow 3 subgroup that we're looking at. And they're the same. They have 100% overlap. And that's a contradiction because I'm assuming that I've written down my distinct Sylow 3 subgroups here. These should be 10 different Sylow 3 subgroups. We shouldn't have any 2 of them that are the same. So we conclude, therefore, that the size of the intersection is actually 3. Because it's not 1 and it's not 9. The only other divisor of 9 is 3. What I'm going to do, therefore, is I'm going to pick an element, x, that's not equal to the identity element in that intersection. I'm going to pick this element x, some non-identity element in that intersection. By the way, you'll note that P sub I and P sub j, they are abelian as groups in their own right, because the size of these two Sylow 3 subgroups are both 9, and any group of size prime squared is always abelian. And I am now grabbing an x that lives in that intersection, and so that means that x commutes with everything in Pi and with everything in Pj. In other words, if we look at the centralizer, remember the centralizer of x, that is all of the elements of G that commute with x. And this contains P sub I and P sub j, but in particular it contains P sub I. In other words, P sub I is a subgroup of that centralizer. Okay, so P sub I is already a subgroup, and since it's inside of the centralizer, everything in P sub I commutes with x. Since x is inside of P sub I, we get this relationship. And that actually tells me something, because the size of a subgroup has to always divide the size of a group. So the size of the centralizer of x is a multiple of 9. This is by Lagrange's theorem. The size of a subgroup must divide the size of the group that it is inside. So the centralizer contains this subgroup of size 9, so its size must actually be a multiple of 9. However, we can actually say even a little bit more than that. Because if I form the product P sub I times P sub j, even that, which consists of all products of elements from Pi and Pj, anything in there also commutes with x. Because again, x commutes with everything that's in either one of these two subgroups. Right? So this guy here is actually, this entire product is contained within the centralizer of x. But the size of this thing, this is a well-known result that can sort of be assumed. The size of this thing is given by this formula right here. And what you'll notice here is that this is 9 times 9 divided by 3, which gives us 27. There are at least 27 elements, therefore, that commute with x. In case 2. We are still in case 2. In this case, therefore, the size of the centralizer of x is at least 27. It's a multiple of 9, but it's also at least 27. And one more thing about it is that the size of the centralizer, since it's a subgroup of G, it has to divide 90. So what numbers do you know that are at least 27, but which divide 90, and which are also a multiple of 9? There's a lot of constraints. It actually tells me that the actual size of the centralizer of x is either 45 or 90. Those are the only two numbers that are at least 27, divide 90, and are a multiple of 9. But I am now going to hopefully convince you that both of these lead to a contradiction. If the size of the centralizer is 45, in the first case, so this is a subcase here, if that centralizer has size 45, then it is a normal subgroup because it has index 2. In this case, this is a normal subgroup by the index 2 argument, and that contradicts the fact that G was supposed to be simple. We assumed that G is simple. It has no normal subgroups other than E and the whole group. The other possibility is that the size of my centralizer is 90. That actually would mean that X commutes with everything in G. And that would mean, by definition, that X is in the center. Do you remember from the start of this proof, when we assumed that G was non-abelian, its center is not the whole group, but if it was a proper subgroup of G, it would be a normal proper subgroup, and that would contradict simplicity unless the center was trivial. But this is now saying that the center not only has E in it, but it actually has X in it as well. The center is not equal to E, but it's not the whole group, so it violates simplicity of G as well. It produces a normal subgroup of G that is proper and non-trivial. This is also a contradiction, because the center is always a normal subgroup.